Welcome back to the channel for practice problems for actuarial exams. Today we will have a problem for exam MFE, and I just want to remind you that I use this smarturl.it redirect service. You can find information on various things by going to smarturl.it / and then whatever word I associated with things that you would like to look at. So for example, if you want to look at this YouTube channel, go to smarturl.it / pass actuarial exams. If you want to look me up, just go to smarturl.it / Jedi. If you want to look at the actuarial program at Illinois State University, go to smarturl.it / actuary. And if you'd like to make a donation to help our students, then please go to smarturl.it / help ISU actuary. Okay, so the problem is a bit longer than usual problems. I showed you it has a graph. I'll go back to the next page with more information in a moment, but we have a Black-Scholes framework that we're working with. We're considering a one-year European contingent claim on a stock. You are given that the time zero stock price is 45, the stock volatility is 25%, 0.25. The stock pays dividends continuously at the rate proportional to its price. The dividend yield is 3%. The continuously compounded risk-free interest rate is 7%. And you're looking at a contingent claim, some kind of derivative security, for which the payoff at time 1 is given by this graph. So take a look at it and think about what it means. Notice that if you had a payoff that is a straight line that goes up has a slope of 1 from the origin to 0.4242, if it continued, if it was just straight up, that's a payoff of just holding the stock. But that's not the case. It stays at 42 after that. After 40 reaching, when the price of the underlying of the stock reaches 42. Calculate the time zero contingent claim elasticity. So the key issue here is figuring out what this contingent claim is. So if the payoff were simply a straight line, as I said before, it would represent a payoff of holding the underlying stock, but without its dividend. Because if you hold a derivative security, you don't get the dividend. And this represents the payoff at time 1 at exercise. So all the dividends in between, you don't get them. Okay. And this is modified at the price of 42 when the payoff becomes a flat $42 for any value of the price of the stock at expiration of the contingent claim. And that price is denoted as of 41, being 42 or above. In other words, any excess of the price of stock S of 1 over 42 is taken away when S of 1 is greater than 42. And what do we call something that pays you the excess over 42 if the price is over 42? Well, it's called a call with exercise price of 42. So what we have here is the stock, although it's the value of the stock at expiration, so no dividends in between. But you take away the excess over 42 at the level of 42. In other words, you take away the call with exercise price of 42. Okay, so the payoff is the price of a stock at time 1 minus what the payoff for a call with exercise price of 42, a European call, because it's a European security, that's what we are told. And the question is about elasticity. Okay, what is elasticity? Well, you need to remember that. That's one way to remember that it's delta of that security times the price of the underlying divided by the price of the derivative security. So in this case, if I write V for the price of the contingent claim, considered as a function of S, and S is the price of the underlying, then it would be the delta of that contingent claim times S over V. It's the same as the partial derivative of the natural logarithm of V with respect to the natural logarithm of S. It's a bit more complicated form of expressing it, so you probably want to remember this more or less standard definition, which is the right-hand side of this equation. Notice that I'm using notation V for the derivative security or contingent claim that we're working with. I'm doing this because we observed that this derivative security can be expressed in terms of a stock and a call, so I'm going to use C for the call and V for this guy. Okay, so if we write C for the price of the call, the price of this derivative security that we're working with is S times e to the minus delta t minus C, based on what we concluded by looking at the payoff. Well, okay, then this means that the partial derivative with respect to S is e to the minus delta t minus the delta of the call. So the elasticity that we are looking for is that delta of V times S over V, and V is S e to the minus delta t minus C. So because the delta of V is expressed in terms of delta of C, if we find all this data from what we know about C, we should be able to plug it in and get the answer. And we are told we are working in the Black-Scholes framework, so we can use Black-Scholes formula for the price of the call, and then to find its delta. Well, the call price in the Black-Scholes framework, in the Black-Scholes model, uses the Black-Scholes formula, which is the prepaid forward price of the stock, or price of the stock without the dividend, times n of d1, where n is the cumulative distribution function of a standard normal distribution, minus present value of exercise price under risk-free rate, times n of d2, and d1 is the natural logarithm of the ratio of this prepaid forward price of the stock to the present value of exercise price, plus 1/2 sigma squared t, of the whole thing divided by sigma squared of t. And d2 is, well, it's almost the same thing, but it has a minus there. So that d2 ends up being the same as d1 minus sigma square root of t. Okay, and here is the data that we have. T is 1, S is 45, K is 42, R is 0.07, delta is 0.03, and sigma is 0.25. So D1 is, well, it ends up being approximately 0.56. What we get when we plug it all in, D2 is approximately 0.31. And the price of the call is what we get when we plug it all in. Note that on the exam you'll have the normal distribution calculator that you can use for the finding of this n of d1 and n of d2. And we get the price of the call to be about 6.75757067. And the value of the derivative security is the ex-dividend or prepaid forward price of the stock minus the price of the call. So it's about 36.91. Also that delta of the V, so the partial derivative of V with respect to S, well, that ends up being e to the minus delta minus the delta of the call. And we know that delta of the call is e to the minus delta t times n of d1. And because we have e to the minus delta t in both of them, this whole thing is really equal to the same thing as e to the minus delta t times 1 minus n of d1, or the same as n of minus d1. And In any case, that's 1 minus the n of d1 that we calculated before, so we plug it in and we have this value. Now we plug all of them into partial derivative. The formula for elasticity is the partial derivative of v with respect to s times s over v. We have all of these values now, so we plug them in, and the answer is almost exactly 0.34, which is answer C. And you need to know the concept of elasticity for the test. It's definitely on the test, and of course you have to have the Black-Scholes formula memorized. So the question for you is, well, did you memorize it? Okay, here it is again. The formula for the call, Black-Scholes formula. You need to remember it. And here it is with the formulas for D1 and D2. So let me make a suggestion about how I remember the formula. I think about it as a lottery ticket formula. No, it's not very precise, I know, but if you have a lottery in which you can win $1 million, and the chances of winning are 1 in a million, what's the fair price for the ticket? Well, it's 1 over a million times a million, so it's about a dollar, right? And of course there could be some provision for profits or things like that, but everybody knows that it should be a dollar because it's a million times 1 over a million, and they're going to take some extra money because they're greedy or whatever, whoever runs the lottery. And of course, that to some degree, greed is productive here if they provide the lottery, although lottery is generally not productive by itself. Irrelevant. The point is that everybody knows how to calculate this fair price of the value of the lottery ticket. But let me ask you this. What is the payoff? So the payoff in the lottery is a million. What is the payoff here if you wait until the exercise time? Well, it's going to be S minus K. And the present value of that S, since you don't collect a dividend, is effectively S times e to the minus delta t. And the present value of the exercise price K is K e to the minus RT. So it's a difference of the two that you have here in terms of their present value, just like the difference is at the payoff time. But they're both modified by probability. N of D1 and N of D2. These are probabilities. Just like the lottery ticket payoff of $1 million is modified by probability of 1 over a million. So it's maybe like 2 lottery tickets, 1 positive, 1 negative, but still the same idea. You must remember this formula for the test. And I think that thinking about lottery ticket from now on should help you remember it. Please remember this is copyrighted material, and also that problems from all actuarial exams are copyrighted to the societies that provided the exams. This is a practice problem from Society of Actuaries, so it is their property, reproduced here with permission. And good luck in your studies, and good luck on the test.